Today we'll be learning about Cantor's diagonalization argument. This proof is a key structure in understanding formal mathematics and philosophy. It gives us a structural idea of how there are some things that are always going to be beyond our scope of proofs. Now, I will be writing down few statements that give you a general surface idea of what exactly Cantor is trying to prove. Cantor is arguing here that there are some infinite sets that are bigger than the set of natural numbers, like for example the real numbers. Now to construct a visual proof, we will be writing down few real numbers between 0 and 1. As we all know, there exists infinite real numbers between 0 and 1. We only have to show that we cannot count them with natural numbers by creating a number that is bigger than the set of natural numbers. Let me show you visually what exactly that means. Now, as you can see, I have marked each number on the diagonals and also mapped each number to a natural number up to infinity. This means that we have marked every number between 0 and 1. But now is the tricky part. We will construct a new number which will be not yet mapped to all these counting. To create this new number, we will take each and every diagonal number and add 1 to it. Now this new number 0.258469 that you see on the screen is the new number we have constructed. Now the next part of the proof is to argue that it is a unique number, meaning it has not been counted before in our list. And here is the fun part. If we compare this number to all the previous numbers, it's always going to be different on the diagonals because we created this new number by adding 1 to each diagonal. Even if all the numbers after the decimal are same, the diagonal number is always guaranteed to be different from the original. Now let's discuss about Turing machines. And with the previous proof, introduce a new idea that there are always going to be some truths that cannot be proved. A Turing machine recognizes and decides a language. The proof given by Cantor tells us that there are some languages that are undecidable. The analogy of words is very important here. You can think decidable as to prove something and recognize as to know something, like a truth. Now, similar to Cantor in abstract mathematics, we have got Gödel, who showed the incompleteness theorem, which states that a consistent system cannot prove everything within its boundaries, or there will be languages which cannot be decided by Turing machines. For example, the statement is false. We cannot decide if this is true or not, because this statement is a consistent logic, which we will talk about in future videos. Now, let M be the set of all possible Turing machines, and W be the set of all possible inputs. Now, let's make another matrix similar to our proof of Cantor sets, and the value this time is going to be 0 or 1 instead of real numbers. 0 symbolizes that the Turing machine rejects the input W. A 1 means the Turing machine accepts it. Now similarly here we will flip each and every diagonal element. As you can see, the diagonal elements 1, 0, 1, 0, 1 when flipped becomes 0, 1, 0, 1, 0. Now in the next part of the proof, we will have to prove again that this is a valid number that exists. That means it is a valid language that exists. Now this part will be tricky, so pay attention. The first assumption is that there exists a Turing machine that can decide this language, and then we will define this language in such a way that it is undecidable, which will become a contradiction to our assumption that there exists a Turing machine that can decide this language, hence proving that there is no Turing machine which can decide this language since it is undecidable. It became very confusing, let me clear it. So, I define this diagonal language as D, where MK does not accept WK, meaning this language will only accept the words when the Turing machine doesn't accept the word. Now the first case of this language is when the Turing machine doesn't accept the word, meaning the Turing machine has rejected WK. But when WK is rejected by this Turing machine, means that it is also not in this language. But that is opposite to our assumption. We define this language as where it will be accepted by the D. So here there is a contradiction. Now the second case is opposite to the first case, where the Turing machine accepts the word input. Now if the Turing machine accepts the word WK, that means that WK is in the language. But look at how we define D. We said D is defined as a language which only accepts the word when MK does not accept WK. So here WK shouldn't be in the language, but here the Turing machine has accepted it, so it's supposed to be in the language. Now this is a contradiction. The final conclusion of this proof is that there exist languages which cannot be decided. Or, the analogy of this statement is, there exist truths that cannot be proved. In the next video, we will be talking about paraconsistent logic and the deeper meaning behind it, how we can solve statements like this statement is false and its Boolean logic behind it.